Thank you. So today we're going to talk about graphs of functions. Today is the 23rd. So can anybody remember for me, what is the definition of a function? How is it different from just any relation where we take two sets and we relate them through some function rule, right? How is a function different from just any other relation? What makes it special? Anyone remember? Okay, so it's a relation. Let's just go ahead. Let's write down the definition again, make sure we have it. It's a relation, so it's a rule that relates two sets, right? A relation that pairs each element of the domain, one of the two sets, right? With only a single element of the range, right? Which means if I say, like, what is f of 2, right? There's only one answer to that question. There's not two different f of 2's, right? Or f of 3, or f of 5, or f of whatever, right? But on the other hand, can members of the range, can there be more than one possible time that we reach the same y value? Or that we have the same y value? That's okay, right? So members of the range can be paired with more than one member of the domain, but not vice versa, right? Every value of x in a function has to correspond to only a single value of y. All right, so graphically, what does that mean? Right? So for instance, let's look at examples of functions and examples of things that aren't functions. We'll look at their graph, functions defined by equations. So for example, the function, I'm just going to list off some and we'll go ahead and graph them. We know that linear functions are all functions, right? Let's look at the graph of x squared plus y squared equals 9. What's that? It's a circle. We know that's not a function, right? So we'll look at the graph of that one, and try to think of what we might need to do there. What's another function that we can think of? Let's go with y is equal to just regular old quadratic. Y is equal to x squared. How about, what's another one we could use? Circle, parabola on the side. Let's look at y squared is equal to x plus 2. That's also not going to be a function. Well, shouldn't be, right? And let's go ahead and look at the graphs of these four. So we have our linear function 2x minus 3. Let's go ahead and graph that. That has a slope of 2 and an y-intercept of negative 3. And so it looks sort of like that, right? Now, this is a circle, right? So it roughly looks like that. The next one here, we have a nice little parabola. And then lastly, we have this one right here, which is, instead of having this be x, just to make this even simpler to graph, I'm just going to make this y squared is equal to x. And so this is going to look like that roughly. It's going to hit the origin here. I'm saying I can't actually get quite there. You know what? Let's try that again. It's weird that I can actually erase that. Make this black. And there we go. All right, so these are the graphs of these four functions. We know from sort of personal experience that from our experience dealing with these things algebraically, if I solve for y with this function right here, right, what am I going to get? Y is going to equal what? How do I solve for y on that one in the lower left-hand corner there? Lower right-hand corner, sorry. Take the square root of both sides, right? What type of square root do we need to take? The plus minus, yeah. And so y could either equal plus or minus x. So this is a situation where if I plug in a specific value of x, I get two possible values for y. There's, in every case, two elements of the domain x paired with a single element of y. So that can't be a function. And the same is going to be true of the circle, right? If we solve for y with this one right here, right, we are also going to end up getting a plus or minus the square root of something. And there's going to be two possible answers if I plug in a certain value of x. And so graphically, how does that end up sort of showing up graphically, that fact that it's not a function here? Because these two, right, this is a function, this one's a function. Sorry, whoops, that is not. This one's not a function. This one is a function. This one's not a function. Can anyone come up with like a graphical rule for how we can tell just by looking at the graph of the function, or the graph of the relation, I should say, whether it is a function or not? Yeah, exactly. So if I draw a vertical line through any part of the function, if it touches more than one point on the function, like right here I draw a vertical line and I'm touching 2 points in the function, that means that this value of x is paired with this value of y and this value of y. And therefore it violates the function rule. So the vertical line test, if you can draw a vertical line anywhere on the graph and have it touch more than 1 point in the function, and the relation I should say, then it's not a function, right? Whereas with my linear function here, it doesn't matter where I draw a vertical line, I'm never going to touch more than 1 point in the function, right? With my quadratic function, the same thing's true. I can draw a vertical line anywhere I want, and it's never going to touch more than 1 point in the function. On this one right here, this sort of parabola on its side, it violates the vertical line rule, right? If I draw a line like right here, then this value of x is paired with this value of y and that value with y, therefore it's not a function. And that, of course, is the vertical line test. So the vertical line test says if you can draw a vertical line, you can draw a vertical line and have it intersect more than 1 point of a relation, then the relation is not a function. So, vertical line test. That's the first thing. Is a function, or is it not a function? Now, if we're given the graph of a function, the question is now, can we identify specific properties of the function just by looking at its graph? So let's look at an example of that. Okay, so let's go ahead, start with the graph of a function. Right, and I'm just going to go ahead and plot some points here. I'm going to say that this intercept right here is the point 7, 0. Let's say this right here is the point 3, 2. This is the point down here. 3, 0. This will be 5, 0. This will be 8, 0. This point right here is going to be 6, 1. And then I'll put, let's say, a point down here. and this will be 0.9, negative 1. All right, so we have a function. I've given you the values at various points along the function. And we're going to go ahead and answer a bunch of different questions about this function now. What color will I do this in? I guess I'll do it in blue. So, first of all, what is f of 3, f of 5, and f of 9? Right? Assuming, and I should have named the function, assuming that this is the function f of x. Right? This is the function f of x where we don't know what the formula is for f of x. It's just y equals some, expression in x. But we do have the graph of said function. So how do I answer these questions? F of 3, f of 5, f of 9. Normally I answer this by plugging that value of x into the expression that we have for the function. But I have no algebraic expression for the function. So how can I use the graph to accomplish the same thing? What do we think? What's f of 3, for instance? What is that asking me? What is f of 3, that statement saying?
What does y equal?
And when x equals?
That number?
3, right? Yeah, so what does y equal when x equals 3? Oh, did I screw something up here? Yeah, it should be 4, 0. That doesn't really make sense, does it? All right, so what would f of 3 be? What does y equal when x is equal to 3?
2.
Y equals 2, yep. What about f of 5?
0.
F of 9?
-1.
Yep, so we can just look at the graph of the function, figure out where x equals 9, where x equals 5, and where x equals 3, right, in each case here. And the accompanying y value is equal to f of 3 and f of 5 and f of 9. That's because these are all going to be spitting out or actually representing the y value when x equals whatever the argument, we call the independent variable the argument sometimes, whatever the argument happens to be. Okay? Let's go ahead and say that, I'm going to have to skip the domain and range questions for now. I'll have to think of a better function for that. Looking at my function right here, what are my x-intercepts of this particular function? X-intercepts, by the way, are also often referred to as zeros. What are my x-intercepts?
4, 0, 5, 0, 8, 0.
4, 5, and 8, yep. And you can either list off the actual points, but if they're x-intercept, it's always implied that the y value has to be 0, right? So you could either just say 4, 5, and 8, or you could actually list off the points. What about the y-intercepts, which are not ever referred to as zeros, on the other hand? The y-intercepts are what? Or intercept. How many y-intercepts are there? 1, right? Is it possible for a function to have more than one y-intercept? Because then it wouldn't be it would fail the, yeah, so it has to, if it is a function, if the relation is a function, its graph should only have a single y-intercept, which in this case is 7. Let's see, where am I gonna, maybe I can just copy this and move on to the next page. Actually, I'll just use a different, I'm going to use a different graph entirely here. So let's go ahead to the next. Okay, and so I'll have a new function that's going to look like this. Whoops, that's not going to be good. I guess I'm going to have to plug this in. I've been spending all day uploading stuff and I forgot to plug it in. So sometimes that happens. Let's do this. Oops. All right, so let's say this top point here. So I'm going to go ahead and once again just list off a whole bunch of points. Let's say that's to, whoops, the point 0, 2. This is going to be the point 2, 3. This will be the point right here. This will be 4, 1. Oh my God, that looks so bad. 4, 1. This is going to be the point 6, 2 again, I guess. Let's say over here. This is going to be the point 6, 7. Let's say 8, 2. This point right here will be 7.5. And then I guess I'll give the x-intercept as well, which will be 9, 0. Okay, so we have a whole bunch of different points on this particular function. Oh, I'll give this x-intercept too. That'll be -1, 0. All right, so in this particular example right here, can you know? So we spent a lot of time on Friday, identifying the domain of a function, right? All the different possible values that x could be, and we did it by looking at the formula for the function, not the graph of the function, right? And what did we do? What was the whole process of finding the domain of a function? If I give you the y equals 3x minus 7 or something like that, how do I determine what the domain of the function is? What did you do in the homework class over the weekend here? Anyone?
So where we just do the second calc and then find the zeros?
No, we're not finding zeros there. If I want to figure out the domain of the function, all the possible values that x gets to, what do I do? Like, for instance, if I gave you the function y is equal to x minus 2 over x plus 3, how would you find the domain of that?
So x plus 3 equals 0.
Yeah, so you're finding the domain by doing what? Finding all the places where the function is,
Real.
or it is, you're doing it by elimination, aren't you? You're finding all the places the function is not defined or not a real number, right? And those points, those values of x have to be taken away from the set of all real numbers to give you the domain of the function. I want to figure out all the values of x that if I plug them in will spit out real number values for y, right? So if the denominator is 0, that's not going to be the case. If with the square root of a negative number, that's not going to be the case. So we looked at that to try and help us out there, right? Now, in the case of this function right here that you're looking at, we have instead of looking at the equation of the function and trying to determine which values of x will give us non-real values for y, we're looking at the graph of function trying to determine what are all the different values of x that we get to, essentially. So for the domain of this function, how could I describe all the different values that x gets to? And we're going to assume that in this region right here where the function's sort of broken, doesn't connect, that it's not like there's like a graph down here where I have for these values of x, there's some y values down here or way up here that we can't see. There's just nothing for y there. What would the domain of this function be? And express it for me in interval notation. What are all the possible values of x that will spit out real number values for y? This is the real plane, right? And so if there were a real number value for all of these x values right here in between this point and this point, they'd be on the graph here. So what's my domain going to be?
Open, infinity, comma, 7.
Yep.
Open. And then 8, open, comma, infinity, open.
And the only thing I'm gonna say these are closed dots here, which means the same thing in a two-dimensional graph as it does like in an inequality graph. If those are closed, then should this be, if 7 and 8 are actually represented there, what should we do for
Yeah.
these?
Yeah, brackets.
Yeah, whoops. What symbol should we connect this with? Union, yes. So the domain is negative infinity to 7, union 8 to infinity. The union of those two sets will give me the actual domain of the function. Now the range is asking, what is the set of all the values of y that we get on this graph? Just like the range is asking for what's the set of all the values of x that we see represented. Are there any values of y that we don't get to ever because of the nature of this function? And we're going to assume that because these arrows both go down here, that it just continues to decrease to the left and decrease to the right here. What would the domain be? Sorry, what would the range be? I take it back. Are there any values of y that we're not going to get to in this function?
Anything above 3.
Yeah, anything above 3. So how would I write that in? Anything above 3 is not in the range, right?
Yeah.
So how would I write that?
Y is less than or equal to 3.
Less than or equal to 3. How would I write that in interval notation?
So open negative infinity.
Oops. So going on all the way to negative infinity, yep.
Comma 3. Close.
Yep. So my range should be negative infinity to 3. Let me ask you the question, what is the solution to this next equation? Say f of x equals 2. What is the solution to the equation f of x equals 2? What are all the possible values of x that would be true for that statement where f of x is equal to 2? Just by looking at the graph. 8, 6, and 0. Yep, there's 3 places where that's where the f of x, which is just a fancy way of saying y, right, is equal to 2. That occurs here, here, and here. So yes, 8 or 0, 6, and 8 are the 3 possible solutions to that. I really would like to, maybe I can just copy this. Okay, this is me trying a new feature right here, I think. No, I'm just going to go with a new graph. All right, so because I can't fit anything else in here, actually, I can fit one more thing in, I guess. Let me ask you this question. For what values of x, now I asked you, for what values of x is f of x equal to? For what values of x is f of x greater than 0? So that, what is the solution to that inequality? And as usual, give it to me in not inequality notation, but give it to me in integral notation. What's the solution to that particular inequality? Where is f of x greater than 0? What does that mean graphically, that f of x is greater than 0?
It's the parts of the graph where it's above the x-axis.
Yeah, so where's the graph above the x-axis? And defined, of course. We should. To be greater than 0, it also has to be a real number. So
Open bracket -1, or yeah.
Yep, because at -1 it is equal to 0, right?
Yeah.
So that wouldn't be part of the set, because that means it's not greater than 0. Yep, so it should be open, comma.
7 closed.
Yep,
Union
yep,
closed 8 open 9, or 9 open.
yep. Perfect. So we're asking essentially where is y greater than 0? Where are we above the x-axis on the function? So I can fit one more in here. Where does the graph of y equals the graph of y equals 3 intersect the graph? Whoops. barely going to be able to fit this in. Where does the graph of the line y is equal to 3 intersect the graph? At the point 2, 3, yep. So we could go ahead and we could draw a horizontal line, the graph of y is equal to 3 at the value where y equals 3, and it's going to just barely touch the graph right there, right? So the point 2, 3. Okay. And just by looking at this, we can list off all the intercepts, right? I'm not going to write them down because I don't have room, but what are my, what's my y-intercept?
0, 2.
2, yep. What are my x-intercepts? And 9. Yep, -1 and 9 are my x, and those are my 2 intercepts there. All right. So let's go ahead and we're going to look at this from the other direction now. Actually, this would be a good point to break because we're sort of halfway through the section here. So let's go ahead and let's break, and then we'll come back. So take a 5-minute break here. So if you actually have the graph of the function, as we did in the previous examples, you can go ahead and analyze the graph of the function just by looking at it. But let's say you don't have the graph of the function. Instead, you have the equation of the function. For instance, maybe you have the function f of x equals x plus 3 over x. Let's say x minus 5. Let's get crazy. All right. You have the formula for the function, but you don't have the actual graph of the function, but then you're asked all sorts of questions about the graph of the function. And the question is then, okay, well, how do you answer questions about the graph of the function if you don't have a graphing calculator and all you have is a formula? And let's say this is a type, and this function right here is what we're going to, in the future, call a rational function. And we don't really know how to graph it yet. But despite that, we're still going to be able to answer basic questions about its graph without even having to graph it. Just like we did in the previous examples, except this time we don't have the actual graph. All right, so for instance, is the point, here's a really basic question, is the point 1, let's say 2, on the graph of the function? Now, if we actually could see the graph of the function, we could just look for the point 1, 2 on the coordinate plane and say, does the function cross through that point? But we don't. So what method can we use algebraically to determine if the point 1, 2 is on the function? And 2 and for y, yeah, f of x, yep. And if we end up with a true statement after we go ahead and simplify everything, sorry, we'll know then that at that point it is actually on the function. So we end up getting 4 over -4, and so we get -1. Is 2 equal to -1? No. So the point 1, 2 is not on the function. What point with an x value of 1 would be on the function? Based on this information. If x equals 1, what does y equal in this function? -1. So the point 1, -1 is on the function, on the other hand. So we can determine if a point is on the function as long as we have the equation of the function, even if we don't have the graph. And even if we have no idea what the graph might look like, we can still figure this information out, right? Let's look at another example here. Different questions about it. Let's keep rewriting it, I guess. Disadvantage of having a very small whiteboard. So that sort of answered another question, which is if x equals 2, what is the corresponding y value on the function. Right? If f of x, let's say, equals 2, then x equals what? Whoops. So I'm asking sort of the opposite question. When y is equal to 2, what does x equal? Here I'm saying when x equals 2, what does y equal on the function, on the graph of the function? Right? So why don't you go ahead right now and try and answer both those questions for me, just using the formula. So if x equals 2, what is the corresponding y value? So that, which would mean that we would have the x and the y value of a specific point in the function. And when f of x equals 2, what does x equal? Right? So, for this first one, we didn't remember to record, but for this first one right here, if I want to find the corresponding y value when x is 2, I go ahead and plug 2 in for x here, right, to get what is essentially f of 2, right? Or not essentially, it is. And that gives us this, and ultimately that gives us negative 5/3, and we reduce that. So negative 5/3 is the corresponding y value when x equals 2. Now, for solving the equation f of x equals 2, we're going to plug 2 in for f of x to obtain the equation 2 equals x plus 3 over x minus 5. And then we can go ahead and solve this equation to answer this question, what is x equal to? So how do we solve a rational, this is called a rational equation because it involves an algebraic fraction. How do we solve this type of rational equation? What do we think, guys? The 2 or the whole thing? Yeah, so you want to, what you're trying to accomplish is to clear out this denominator, to get rid of the denominator of this fraction, because then you will no longer have an algebraic fraction. And we always like to try and get rid of fractions if we can. It makes it much easier to solve this. So if we multiply the whole thing by x minus 5, we will get 2 times x minus 5 is equal to what?
X plus 3.
Yeah, because right here, the x minus 5's cancel, right? On the right side there. And so we'll end up with 2x minus 10 equals x plus 3. And then if we go ahead and subtract the x from both sides, we get x, and add the 10, we get 13. So x equals 13. So that's a little bit of a review, of course, of solving rational equations, for those of you who haven't seen those in a while. But that's not so bad, right? All right, let's answer one more question, or 2 more questions about this same exact function here. Questions about the graph of the function, just so we have it. So the function f of x equals x plus 3 over x minus 5. Let me ask you this question. What are the x and y intercepts of the graph of f of x? So go ahead and answer me, what are the x and y intercepts of the graph of f of x? God, I just can't remember that. So, to tackle finding the x-intercepts, we're going to start off by setting f of x, which is the y value, equal to 0, because we know on the x-axis, that's where y equals 0, right? Which we know f of x is in turn equal to x plus 3 over x minus 5. So how do I solve this equation? 0 equals x plus 3 over x minus 5. What do we think, guys?
Multiply the whole thing by x minus 5.
Yep. And the thing about this is that x minus, so if we multiply the whole thing by x minus 5, 0 times anything is 0, right? So we get 0 equals x plus 3, and so x equals negative 3. So negative 3 is going to be the x-intercept. Now the y-intercepts occur when what is true?
X equals 0.
So to find the y-intercepts, we want to find f of 0, right? Which will be 0 plus 3 over 0 minus 5. So the x-intercept is going to be negative 3/5. Y-intercept. The x-intercept is negative 3. The y-intercept is negative 3/5. Right. So we've determined a whole bunch of information about the graph of this function, which we don't really know much about this type of functions, rational functions yet, so we haven't talked about them. You guys haven't seen them because we don't cover them in Algebra 2. You've probably seen them a little bit in Algebra 2 honors, but we haven't really talked about how to graph them yet. We're going to talk a little bit later about their asymptotes, which is one of the big characterizing things of rational functions. But you don't even need to know that. So these rules that we're using right now apply to any function, no matter, right, what type of function they are. And that's going to be the whole theme of what we're doing here in this chapter, is developing all these universal rules that apply to every single type of function, no matter what family of function it falls in, whether they're linear, quadratic, logarithmic, exponential, trigonometric, rational, polynomial, all of which we're going to cover. And that's what's so nice about it. Okay, we went through this a lot faster than I thought we were going to, so I'm actually going to go into section 2.3 a little bit today. I caught myself this time. So, we're going to start talking about properties of functions. And the first property of the functions we're going to talk about is symmetry, right? So we have three different functions that I've written out here for us. One's sort of a parabola, one's a parabola on its side, and one is, well, it sort of looks like the graph of a cubic function. And let's talk about the type of symmetry each of these graphs have. So the first graph here, we see that if we were to fold it around the line of the x-axis here, or the y-axis, sorry, it would line up perfectly on top of each other. So what type of symmetry do you think this one has?
Rotational symmetry.
About what? Well, all symmetry is really rotational, right?
Horizontal symmetry.
It's all symmetry is rotational. So if if I take the graph, like say, take the actual graph of the function, I fold it along the y-axis, like so, they're going to line up on top of each other. What axis am I folding it or rotating it around? The y-axis, right? So we're folding it around the y-axis, and it's symmetric about the y-axis, right? So this is going to be y-axis symmetry. And in this case, if this is the point xy, then this would be the point negative xy, right? So to have y-axis symmetry, right? To have y-axis symmetry, if the point xy is on the graph of the function, the point x negative y must also be on the graph of the function. So that's y-axis symmetry. This next one, I bet you can guess, is what type of symmetry?
X-axis.
Yeah, if I fold it along the x-axis, and I get the same thing, it's x-axis symmetry, right? And so if the point, once again, if the point xy is on the graph of the function, what other point should also be on the graph of the function?
X negative y.
X negative y, yes. And in fact, something with x-axis symmetry, is it a function? No, anything with x-axis symmetry is actually not a function. Still a relation, but not a function. And lastly, could I rotate part of this function in a way that it would end up on top of the other part of the function? What if I take this piece in the first quadrant and I rotate it around the origin, and I rotate it around the origin by 90 degrees? Wouldn't that line it up with this one down here? So if I'm rotating it around the origin, this is symmetry about the origin is what we'll call this. Symmetry about the origin. And so once again, if the point xy is on the function, what other point must be on the function?
Negative x negative.
Yep. Okay. So these are the three types of symmetry that we're going to talk about. Y-axis symmetry, x-axis symmetry, and origin symmetry, right? And it turns out there's going to be an algebraic basis for two of these three types of symmetry based on functions that we're going to see. And the first one is whether is a function being even. So let me go ahead and, first of all, this is a definition. A function is even if, if f of negative x is equal to f of x. So at opposite values of x, we have the same value of y, right? What type of function, of the three types of symmetry we talked about before, which type of symmetry does that sound like? For opposite values of x, we have the same value of y. Can you think of a function where that would be true? Yeah, that's y-axis symmetry at work there. So let's go ahead and graph my y-axis function. So this is the function where we said if the point xy is on the function, we also said the point that negative xy must also be on the function. And what this is telling me is that f of negative x equals f of x, right? Because they have the same y value. Does that make sense? So if a function is even, it has y-axis symmetry. Now, the definition of an odd function . A function is odd if f of negative x equals negative f of x. So if f of the opposite of x equals the opposite of f of x, that one's a little bit trickier. What would that look like graphically? What do we think? If f of negative x is the opposite of the y value at x, I'll give you a hint. That's going to be one of the types of symmetry that we're talking about here. Not x-axis, now, because then it wouldn't be a function anymore. That's origin. Yeah, you only have one other choice. Process of elimination. Right? And we said, this is symmetry about the origin here, that in this case, if the point xy was on the graph of the function, what point must also be on the graph of the function? The point what? Which is the same as saying that f of negative x, right? F of negative x is negative y, right? Which is the opposite of what f of x is, so it's equal to negative f of x. Right? So that's why that results in. So an odd function always has symmetry about the origin. So that's how even and odd functions tie into symmetry. And then x-axis symmetry only shows up if it's not a function, and so it's neither even or odd if it has x-axis symmetry. It just sort of is what it is. And of course, does every function have symmetry? No, there's some functions that are completely non-symmetric. So an algebraic basis for this symmetry to determine if a function is symmetric about the origin or symmetric about the x-axis, I mean the y-axis. Right? Because we do know that there's some functions that are not symmetric. Right? About any axis. There we go. Is that function symmetric about anything? No. Totally non-symmetric function. So this is not, just because we're talking about symmetric functions now doesn't mean that every function is symmetric. In fact, most functions are not symmetric about any axis, but some are, and it's important to know if they are. So let me give you some functions. If you had the graph of function, I'm pretty sure you guys are pretty smart. You can probably look at the graph of the function and tell me if it has x-axis, y-axis, or origin symmetry. But what if you didn't have the graph of the function? What if you had the, once again, the formula for the function? I'm just going to go into a new slide here. So for instance, let's say I have the function f of x equals 3x squared, and another function f of x is equal to x cubed minus x, and then a function f of x equals 2x squared plus 1. All right, so I'll do the first one with you, and then I want you to use that same idea to do the second two. So the first one here, if I'm asking, is this function, in each case I want to know, are the functions even or odd or neither? Right? Even, odd, or neither. And if they're even or odd, we know they have either y-axis or origin symmetry, right? So, what do we think we're going to do to determine whether the function is even or odd? Using the algebraic definition, which was that in the case of an even function, f of negative x equals f of x. And in the case of an odd function, f of negative x equals negative f of x. How would we use those definitions of even or odd to determine whether these functions are even, odd, or neither, and therefore symmetric or not symmetric?
We get 1 and negative 1.
Why don't we do an even, because I can think of a function that has the same value of y for 1 and negative 1, but that wouldn't necessarily be true for all values of x. So let's make it as general as possible and just take f of negative x. Then that will cover every single possible value of x. Because there are functions that it might be true for one pair of values of x, but not for the rest of them, and therefore it's not symmetric. So what we're just going to do is we're just going to evaluate f of negative x, right? Just like we did in the previous section when we were taking, what is f of negative x, what is f of x plus 2, and all this stuff, right? And what's negative x squared? So f of negative x equals 3x squared, which is f of x. And so this function is even. We've proven that f of negative x equals f of x, and therefore it is symmetric about the and this is a quadratic function that sort of looks, whoops, nothing like that. That sort of looks like this. And so we can see how that would have y-axis symmetry, right? Makes sense. Why don't you do the same test on the following two? Determine whether they're even, odd, or neither. If they're even or odd, tell me what type of symmetry they have. And if neither, and if they're neither, you can just sort of leave it. So for this first one, if we evaluate f of negative x, we get the following expression. If we simplify this, negative x cubed is negative x cubed because it's an odd power. These two give me plus x. And that, if I factor with negative, we see it's the exact opposite of this, right? Which means it is the exact opposite of f of x, right? And therefore, this is an odd function. And it has symmetry about the origin. Right? The next one, if we go ahead and evaluate f of negative x, we're going to get 2 times negative x squared plus 1. And negative x squared is equal to what? 2x squared, right, plus 1. And this is equal to f of x, right? It's the same exact thing, and so this is going to be an even function. Oh, I should have put... Let's actually back this up. I sort of fudged up when I wrote this because I wanted it to actually be a neither function. So what if instead of being 2x squared plus 1, let's say that this is instead... Let's say this is instead the function 2x squared plus x, right? Then if we take f of negative x, we get 2 times negative x squared minus x, right? And yeah, we end up getting 2x squared, because negative x squared is the same as x squared, minus x. And that's not the same or the exact opposite of f of x, right? Because the thing about it is, this term is the exact same, and this term is the exact opposite, but the entire function needs to be either one or the other. The function either needs to be entirely opposite, like negative, parentheses around the whole thing, or it needs to be entirely the same, and it's neither of those two things. So this function is neither, and it has no symmetry. So there we go. So the assignment for tonight are the questions as follows. From the old worksheet that I handed out on Friday, the 2.1 worksheet, these questions right here, sort of review. From the 2.2 worksheet, these questions right here. I handed out the 2.2 worksheet today. I also scanned it, turned it into a PDF, and sent it out. And from your book, I'm assigning these questions right here. So these are actually from your new book that you should have. If you don't have it, let me know. We'll talk about it. But these are the homework assignment, this is the homework assignment that will be due tomorrow. Have a good day.